a very simple idea. What happens when you heat up an object? When you warm a piece of metal or a lump of coal, it glows. First red, then orange, then white, depending on the temperature. This glow, called black body radiation, comes from how objects emit electromagnetic radiation when heated. It was easy to observe, and it seemed like it should be easy to explain. And yet, the math refused to cooperate. Classical physics, using the well-known equations of the time, predicted something bizarre. According to the formulas, as the temperature of a black body increased, it should emit more and more energy at shorter and shorter wavelengths, particularly in the ultraviolet range. Problem: this prediction led to infinite energy at high frequencies, a scenario so impossible and ridiculous it was nicknamed the ultraviolet catastrophe. No amount of tweaking classical equations could stop the math from spiraling into nonsense. Reality simply didn't match the predictions. Something was missing. Enter Max Planck. In 1899, Planck was a German theoretical physicist with a reputation for careful thinking. He wasn't particularly radical or rebellious. In fact, he firmly believed in the classical worldview, but he was also pragmatic, and when faced with the blackbody radiation problem, he did something quietly revolutionary. To fix the math, Planck introduced a small, strange idea. What if energy couldn't...
Don't become no murder case now, nigga.
Quanta. This was a dramatic shift from the continuous view of energy held by classical physics. Instead of a smooth flow, energy would arrive in steps, tiny jumps that depended on the frequency of the radiation. Planck even introduced a constant, now known as Planck's constant, to describe the size of these energy packets. It was unimaginably small, but mathematically elegant. When he plugged this idea into his equations, something amazing happened. The infinite energy problem vanished. The equations worked. They matched the real world. Planck had solved the ultraviolet catastrophe. And yet he didn't quite believe it. In fact, Planck himself described his solution as a mathematical trick, a clever way to make the numbers behave, not a description of how the universe actually worked. He assumed that future physicists would find a better explanation that wouldn't require such odd assumptions. Quantization, to him, was a temporary patch, not a fundamental truth. What he couldn't have known at the time was that his trick would become the cornerstone of an entirely new way of thinking. His idea that energy comes in discrete packets laid the groundwork for quantum theory, a theory that would soon unravel much of what classical physics had taken for granted. It's easy to look back and see this as the moment everything changed, but at the time, it felt more like a strange side note than a revolution. Planck hadn't set out to challenge the foundations of physics, he just wanted the math to work, and yet, by introducing quantization, he had lit the first match in what would become a slow-burning fire, one that would eventually reshape our understanding of light, matter, and the nature of reality itself. This humble beginning, tucked into a quiet paper published in 1900, didn't shout its importance. There were no dramatic declarations, no sweeping pronouncements, just a small constant, a new way of thinking about energy, and a curious little fix for a problem that refused to go away. From that point on, physics would never quite feel finished again. By the early 1900s, light was thought to be pretty well understood. Thanks to James Clerk Maxwell's equations, scientists had shown that light behaved like a wave, an elegant ripple in the electromagnetic field. It bent, bounced, diffracted, and interfered just like any proper wave should. And after Max Planck's quiet introduction of energy quanta, Most physicists assumed things would settle down into a new, slightly adjusted normal. But then came a riddle involving metal, light, and a surprising refusal to cooperate. It was called the photoelectric effect, and it worked like this. If you shine light on a metal surface, electrons can be ejected from the metal. The idea made sense. Light delivers energy. Energy kicks out electrons. No big deal. According to wave theory, increasing the brightness of the light should increase the energy transferred to the electrons. A brighter wave should shake electrons loose more effectively. That was the expectation. But that's not what happened. In experiments, scientists found something strange. Shining brighter light didn't necessarily eject electrons with more energy. What mattered most was the frequency of the light. If the light was below a certain frequency, even a very bright light, it did nothing at all. No electrons were ejected. But above that frequency, even a dim beam could knock electrons free with ease. The threshold was sharp and it made no sense under classical wave theory. This little inconsistency became a full-blown mystery. Enter Albert Einstein. In 1905, a year often called his miracle year, Einstein published a paper that changed everything. To explain the photoelectric effect, he proposed something bold. What if light wasn't just a wave? What if, under certain circumstances, it behaved like a particle, a tiny bundle of energy travelling in a straight line? Einstein suggested that light was made of individual packets of energy, which he called quanta of light, later known as photons. Each photon carried a specific amount of energy, determined by its frequency. If a photon had enough energy, it could knock an electron loose from the metal surface. If it didn't, no amount of photons, no matter how many or how bright, could do the job. It was like trying to open a locked door with a handful of keys, none of which fit. No matter how many you had, you weren't getting in. Einstein's idea built directly on Planck's earlier work, but went further. Instead, he proposed something stranger. Light, he said, was both a wave and a particle. It could act like one or the other, depending on how you observed it. This duality wasn't just a weird trick of perception, it was fundamental to the nature of light itself. Imagine a beam of sunlight filtering through a window. It spreads and ripples like a wave bouncing off dust and glass. But zoom in, way in, and you'd find tiny quanta of energy, each with its own frequency, knocking into atoms, changing the world one collision at a time. This idea of wave-particle duality is one of the strangest in all of physics, not because it's complicated, but because it challenges the very categories we use to describe reality. In the classical world, things were either particles or waves, not both, not neither, and certainly not whatever they feel like being depending on the situation. But the quantum world doesn't ask permission to make sense. Einstein's photon explanation of the photoelectric effect not only matched the experimental results, it did so beautifully. The energy of each photon depended on its frequency, exactly as Planck had suggested, and it neatly explained why low-frequency light, no matter how intense, couldn't eject electrons. The individual photons simply didn't carry enough punch. The impact of this idea was massive. In 1921, Einstein received the Nobel Prize in Physics, not for relativity, as many assume, but for his explanation of the photoelectric effect. That's how significant this discovery was. Still, even Einstein found the quantum world uncomfortable. He famously resisted the more probabilistic interpretations that would follow in later years. God does not play dice with the universe, he once declared. But dice or not, the rules were changing, and at the heart of those changes was a strange truth. Light, the thing that illuminates our world, refused to fit into any tidy box. It came in quanta. It danced as a wave. It collided like a particle. It shimmered between states, revealing just enough to keep us wondering, and just enough to keep us unsure. What began as a simple experiment with light and metal ended up shaking the foundations of physics. Because if light could behave this way, both continuous and discrete, both spread out and point-like, what else might be lurking in the quiet corners of the universe waiting to break the rules? Imagine this. You set up a table, place a flashlight at one end, and cut two tiny slits in a piece of cardboard. You shine the light through the slits and look at the pattern it makes on a screen behind them. Not exactly thrilling, right? And yet in this humble arrangement, two holes and a bit of light, we find one of the most mind-bending experiments in all of science. The double-slit experiment has become something of a legend in physics, and not because it's complicated. In fact, it's almost embarrassingly simple. But what it reveals is anything but. Some physicists have even joked that this is the most dramatic science experiment of
violent, aggressive predator who hunts in all kinds of environments.
Starring a flashlight in two holes in cardboard. Let's start with what we'd expect. In the world of classical physics, waves and particles behave very differently. A wave, like water or sound, spreads out. It interferes with itself. Imagine ocean waves passing through two openings in a barrier. The waves emerge on the other side and overlap, creating a pattern of peaks and troughs that can reinforce or cancel each other out. That's interference. It's well understood and predictable. Now imagine particles, like tiny rubber balls, fired at a wall with two openings. Some go through the left slit, some go through the right. They don't overlap or interfere. On the screen behind the slits, you'd expect to see two clusters of impact points, right where the slits are. That's the particle behaviour. Straightforward, no surprises. So what happens when you do this with light? Instead of a constant stream, there are individual particles of light making their way toward the slits, one by one. Now you'd expect these lone photons to act like particles, each going through one slit or the other. And if you wait long enough and collect enough hits on the screen, you should see two bright spots where the particles landed, just like those rubber balls. But that's not what happened. Even when sent through one at a time, the photons gradually built up the same interference pattern as before. A pattern that required waves interfering with themselves. How could a single photon interfere with itself? Did it go through both slits at once? Was it somehow a wave and a particle at the same time? This was no illusion. The interference pattern persisted, suggesting that each photon had travelled through both slits simultaneously, like a ghost of itself, exploring every possible path until it landed. If that wasn't enough to raise some eyebrows, things got even stranger. Physicists decided to peek behind the curtain. They placed detectors at the slits to observe which path the photon actually took. Surely, they thought, we can just watch and settle this once and for all. Did the photon go through the left slit, the right slit, or somehow both? But when they looked, the interference pattern vanished. As soon as the detectors were turned on and the photons were observed, the photons stopped behaving like waves. They acted like ordinary particles again, landing behind just one slit or the other. No more interference, no more ghostly wave behaviour. It was as if the very act of observing forced the photon to make a decision. Go left or go right. No superpositions, no fuzzy in-betweens. Reality had been caught in the act, and it immediately straightened up and acted normal. Turn off the detectors, and the interference returned. Turn them back on, and it vanished again. The implications were staggering. It wasn't that our measuring devices disturbed the photons. These were passive, non-intrusive setups. The issue wasn't how we observed, but that we observed at all. It seemed that the mere knowledge of the photon's path, the potential to know, was enough to collapse its wave-like behaviour into a particle state. Reality, in a sense, cared whether it was being watched. This wasn't just a fluke or experimental error. The double-slit experiment has been repeated countless times, with photons, electrons, even molecules made of hundreds of atoms. Otherwise, the result's the same. Left unobserved, these particles act like waves and interfere with themselves. Observed, they behave like classical particles and fall neatly into line. And if that sounds unsettling, well, you're not alone. This experiment sits at the very heart of quantum physics, and it resists every effort to explain it in familiar terms. It suggests that at the smaller scales, particles don't follow strict paths. Instead, they exist as a spread of possibilities, a shimmering cloud of potential outcomes. Only when a measurement is made does that cloud collapse into something definite. Some have tried to picture the photon as a wave that splits and reunites. Others prefer the language of probability, describing the wave function as a tool for predicting outcomes. And still others, in the many worlds camp, imagine each possibility branching into its own separate universe. But whatever the interpretation, the facts remain the same. Until we observe it, the particle doesn't seem to commit to any one state. What began as a simple test of light has turned into a profound mystery about the nature of reality itself. Is observation an active part of shaping the universe?
You get wild, cheating. Oh, motherfucker. Hey, look out for almost like
ones, rooted in experiment, measured and confirmed. The double-slit experiment doesn't give us clear answers, but it does give us one powerful insight. The universe, at its core, is not a clockwork machine. It's a strange and shimmering tapestry, woven from possibilities, and it responds in curious ways to our gaze. With two slits, a light source, and a screen, we've discovered that the universe winks at us when we're not looking, and stands still when we are. In the world of quantum physics, if there's one piece of math that's whispered through the entire theory like a secret spell, it's Schrödinger's equation. Now, don't worry, this isn't going to be a math lecture. No one's getting out of bed to dream about partial differential equations. But this particular equation is different. It's not just a string of symbols scribbled on a chalkboard, it's the quiet heartbeat of the quantum world. Back in the 1920s, physicists were wrestling with how to describe particles that didn't seem to behave like particles at all. Electrons were showing wave-like patterns, photons were acting like probabilistic ghosts, and the old laws of motion, the ones Newton gave us, just weren't cutting it anymore. The universe needed a new kind of language. Enter Erwin Schrödinger. In 1926, he proposed an equation that described not just how particles moved, but how their wave functions evolved over time. It was elegant, compact, and shockingly effective. And even though it might look like a tangle of Greek letters and operators, at its core it tells a simple story. It describes how a quantum system changes. But let's step away from the symbols and get to what really matters. The key concept here is the wave function, often denoted by the Greek letter psi. If that sounds abstract, think of it like this. The wave function is a sort of mathematical whisper that tells us everything we can know about a quantum system, where a particle might be, how likely it is to be there, how it's moving or might be moving. The wave function doesn't give us hard answers. It gives us probabilities. If you picture a particle as a little dot moving through space, classical physics will draw a neat arrow showing its exact position and velocity. Schrödinger's world doesn't do that. Instead, it gives us a hazy, rippling cloud, a wave, that says the particle is likely to be over here, but it could also be over there, maybe just a little bit up there too. This is where the magic happens. Schrödinger's equation lets us evolve this cloud over time. It shows how the wave function changes as the particle moves, though it's really more like how the possibilities of its position, shift and flow. And when we measure the particle, when we ask, where are you? That wave function collapses. Suddenly the cloud disappears and we get a single definite answer. Reality is profoundly different from the picture of the universe. That came before. Instead of particles tracing predictable paths like planets around the sun, we now see swirling fields of probability, full of uncertainty and ambiguity, until observation pins them down. But let's pull it down to something more visual. Imagine you're blindfolded and standing in a room. Somewhere in that room there's a quiet cat. You can't hear it, can't see it, but you can toss little balls and listen for the sound they make when they land. Over time, you start to build a picture of where the cat might be. Areas with a higher chance, others with less. That mental map we're building, that's like the wave function. It's not a picture of reality as it is, but as it might be. Now imagine you could write an equation that tells you how your map changes over time. Maybe the cat likes to move toward corners or sit near warm objects.
Off the road, little homie.
That equation would be your guide to where the cat is likely to be next. That's what Schrödinger did, except instead of cats, he was thinking about electrons. The actual equation is continuous and smooth. It allows these waves of probability to ripple and shift just like water in a pond. It respects the underlying symmetries of nature. Like energy conservation and time evolution, but it doesn't care much for certainty. It tells us what could happen, not what will happen. And what's fascinating is how beautifully it works. Physicists have used Schrödinger's equation to describe everything from the structure of atoms to the way molecules bond, from semiconductor behavior to superconductors. It even predicts exotic phenomena like quantum tunneling, where particles slip through barriers they shouldn't be able to cross. The equation itself is timeless, gently ticking forward with every moment, offering a map of the unknowable. One of its most famous successes was in explaining the hydrogen atom, the simplest atom in the universe. Before quantum mechanics, no one could fully explain why electrons around a nucleus seem to settle into specific orbits, rather than spiraling inward or wandering off. Schrödinger's equation revealed that electrons aren't whizzing around like miniature planets. Instead, they form standing waves, stable patterns of probability, around the nucleus. These are the orbitals you may have seen drawn as soft clouds or shapes in textbooks. And these clouds are not just visual metaphors, they represent the real, measurable likelihood of where an electron might be found if you decided to look. These aren't orbits, they're presence zones, and they exist only because the electron isn't a simple particle. It's a ripple in a sea of probabilities. It's strange, certainly, but it's also beautifully consistent. Unlike some theories that need patches or caveats, Schrödinger's equation has aged like fine wine. It works. It has predicted time and again the behaviour of the very small with astonishing accuracy. And yet it remains hauntingly abstract. You can't hold a wave function. You can't see it. But it's there, describing the ghostly potential of everything from an atom in your tea to the electronics in your phone. And then there's the philosophical side. What is a wave function really? Is it a description of our knowledge? Or is it an actual part of reality? Something that truly exists until it collapses into one outcome? Different interpretations of quantum mechanics argue fiercely about this, but the equation itself doesn't take sides. It simply does what it does, quietly, reliably, and strangely. Even Schrödinger himself had mixed feelings. While he was proud of the equation, he disliked the idea that particles didn't have definite properties until they were observed. His famous thought experiment involving a cat, alive and dead at the same time, was meant as a critique of the very uncertainty his work had unleashed. He gave us the mathematics of quantum waves, then questioned what those waves really meant. Still, it's hard not to admire what he built. In a world that often demands yes or no here or there, Schrödinger offered something gentler, a shimmer of maybe, a softly pulsing guide to what could be. His equation doesn't shout or command, it suggests, it flows. And in doing so, it reveals a version of the universe that's quieter, subtler, and far more mysterious than we ever imagined. At the tiniest scales, motion isn't always motion, position isn't always position, uncertainty is more of a luxury than a rule. But thanks to one elegant equation, we can still find our way, gently, mathematically, through the haze. In the classical world, the world of apples, bicycles and bowling balls, you can know where something is and how fast it's going at the same time. It's not even a question. A radar gun clocks the speed of a car while GPS tells you exactly where it is. No mystery, no contradiction. But the quantum world doesn't play by those rules. In the 1920s, Werner Heisenberg introduced a principle so strange and so central to quantum mechanics that it still gives students and scientists alike a moment of pause. It's called the uncertainty principle, and it tells us that at the most fundamental level of reality, there are limits to what we can know. Specifically, it says this: the more precisely we know a particle's position, the less precisely we can know its momentum, and vice versa. Now, momentum is just mass times velocity. It's a measure of how much motion something has, and if you think about it in everyday terms, this principle sounds almost silly. How could knowing where something is make you unsure about how fast it's going? If you see a train pulling into the station, you know both its position and its speed. Easy. But at the quantum scale, reality doesn't allow that kind of clarity. This isn't about our measuring tools being clumsy or crude. It's not a matter of needing better technology. The uncertainty isn't in our instruments. It's woven into the fabric of the universe itself. Let's say you're trying to observe an electron. You want to know where it is and how fast it's moving. To do that, you might shine some light on it. But light is made of photons, and photons carry energy. When one of those photons hits the electron, it changes the electron's motion. It's a bit like trying to find a soap bubble in the dark by throwing tennis balls at it. You'll definitely find it, but you'll also destroy it in the process. Still, Heisenberg's point wasn't just about disturbing particles. His principle is built into the mathematics of quantum mechanics. Even if you could observe without interfering, watching through some ghostly, non-intrusive means, the uncertainty would still be there. It's not a bug, it's a feature. At the heart of the uncertainty principle is the wave nature of particles. Imagine trying to locate a wave in the ocean. You can say where the crest is, but the wave stretches out in space. Similarly, a particle like an electron is described by a wave function, a spread-out cloud of possibilities. If the wave is wide and smooth, you can't tell where the particle is exactly, but you can estimate its momentum fairly well. If you narrow the wave to pinpoint the particle's position, the momentum becomes more uncertain. The wave gets choppy. It's a cosmic trade-off, and there's no way around it. The product of the uncertainty in position and the uncertainty in momentum is always greater than or equal to a tiny number. Planck's constant, divided by 4 pi. That number is very small, so in our everyday world the effect is negligible. You can measure the position and speed of a baseball to incredible precision without ever bumping into quantum limits. But at the scale of electrons, atoms and subatomic particles, the uncertainty becomes impossible to ignore. It shapes the very behaviour of the world beneath our senses. If you try to trap a particle in a very small space, to nail down its position, it starts to behave wildly. Its momentum becomes highly uncertain, and it can begin zipping around unpredictably. Try to pin it down further, and it resists even more. It's as though nature doesn't like being told exactly where things are. This is not narrowing the machinery, it's a blur that can't be wiped away. One way to think about it is like trying to hold mist in your hands. The tighter you squeeze, the less you have. Open your hands a little, and more of it lingers. That's the delicate balance between knowing too much and being forced to let go of something else. In many ways, the uncertainty principle is a philosophical warning label on the quantum world. It tells us that knowledge has boundaries, not because of human limitations, but because of how reality itself is built. We are not dealing with tiny billiard balls rolling through space. We are dealing with possibilities, probabilities, and waves that refuse to be nailed down too tightly. This principle also explains why atoms don't collapse. You might wonder why electrons don't simply fall into the nucleus of an atom, since opposite charges attract. But thanks to the uncertainty principle, electrons can't sit still. If an electron were to fall into the nucleus and stay there, its position would be perfectly known, which means its momentum would become infinitely uncertain. That would require infinite energy. Nature says no. So electrons hover, not because they want to, but because quantum rules won't allow anything else. The uncertainty principle creates a kind of built-in resistance, a gentle pushback against absolute confinement. This strange limit also has consequences for measurements of energy and time, or angular momentum and orientation. In each pair, increasing precision in one the light switches on or off. Your tea is hot or cold, though sometimes questionably lukewarm. But in the quantum world, this tidy division of states breaks down completely. Objects at the smallest scales don't always pick a side. They can hover in a strange in-between, a blend of all possible outcomes. This is the realm of quantum superposition. To picture this, imagine flipping a coin. In the classical world, once the coin leaves your hand, it travels through the air with a clear trajectory. You may not know whether it's heads or tails until it lands, but it is one or the other the whole time. It's just hidden from you. Quantum systems don't work that way. In the quantum world, if you flip a quantum coin, it doesn't secretly land on one side while you're not looking. Instead, it enters a state of superposition, a weighted combination of both heads and tails at once. It isn't undecided. It isn't switching quickly between the two. It is genuinely, physically in a state that is both, until you observe it. And when you do, when you check to see what state the system is in, the superposition collapses. The quantum coin chooses a face, and your measurement becomes real. But before you looked, It wasn't just unknown, it was both. That's a hard pill to swallow, and it's not just counterintuitive, it's deeply weird. Superposition was first introduced as a way to describe the behaviour of quantum particles like electrons and photons. These particles, rather than following predictable paths, exist as wave functions, mathematical expressions that describe probabilities. Each possible state, a spin pointing up or down, a photon going left or right, is part of the equation, and all those possibilities coexist until a measurement selects one. You might picture it like a foggy landscape of outcomes. The particle isn't walking a path, it's more like it's spread out, smearing itself across every possible route it could take. When you interact with it, that fog suddenly snaps into a single location, a specific outcome, like lightning illuminating one hilltop in the mist. This concept led to one of the most famous thought experiments in all of physics, Schrödinger's cat. Suppose you place a cat in a sealed box with a radioactive atom, a detector, and a vial of poison. If the atom decays, the detector breaks the vial and the cat dies. If it doesn't, the cat lives. Quantum mechanics tells us that until the atom is observed, it exists in a superposition of decayed and not decayed states. And so, by extension, the cat is both alive and dead until someone opens the box. This wasn't meant to be taken literally. Erwin Schrödinger was highlighting the absurdity of applying quantum rules to large objects. But the idea struck a chord. It painted superposition not just as an abstract idea, but as something with deeply strange implications for what reality is. And yet, despite all the weirdness, superposition is not a flaw in the theory. It's not some bizarre loophole that physicists tolerate. It's one of the most powerful features of quantum mechanics. In fact, much of modern quantum technology depends on it. Take quantum computing, for example. In a classical computer, the smallest unit of information is the bit, which can be either 0 or 1. Everything your phone or laptop does, every photo, every song, every message, is encoded using combinations of these two states. Quantum computers use qubits instead, and a qubit, unlike a superposition is delicate. Quantum systems are easily disturbed. The slightest interaction with the environment, stray photons, vibrations, even air molecules, can collapse the wave function. This process, known as decoherence, is one of the biggest challenges in building stable quantum systems. It's like trying to balance a feather on the tip of a pencil while someone's sneezing in the next room. The superposition vanishes the moment the system interacts with the outside world. That fragility is part of what makes quantum systems so fascinating. They offer power, but only under very precise and isolated conditions. They give us access to probabilities, not certainties, and ask us to rethink what it means to say that something is. It also leads to a deeper philosophical question. If particles can exist in multiple states, is that reality, or just a reflection of what we know? Some interpretations suggest that the wave function represents knowledge, our best guess about a system until we measure it. Others say the wave function is physically real, and the particle truly is in multiple states until it's forced to choose. Either way, quantum superposition invites us to loosen our grip on classical logic. It tells us that opposites can coexist, that a system can be this and that, here and there, yes and no, all at once. That reality, at its core, is not a single thread, but a tapestry of possibilities, overlapping and unresolved until observation pulls one strand loose. It's strange, it's uncomfortable, but it's also beautiful. Because in this strange rule of superposition, we find a universe that isn't rigid, but flexible. Not mechanical, but poetic. It's a world that allows for contradiction and uncertainty, not as flaws, but as features. And in doing so, it opens up new ways to compute, to communicate, to explore, and to imagine what's possible when reality refuses to make up its mind. Imagine you have two gloves, one left-handed and one right-handed. You put each glove into a separate box and send one to the other side of the world. You don't know which box contains which glove, but the moment you open...
Come on, man! Come on, man! Come on! Ah! Ah! Nobody needs to get hurt, all right?
in a certain way, by being created together, colliding, or otherwise becoming connected, they can become entangled. That means their quantum states become linked. Whatever happens to one, in a very real sense, affects the other, even when they are separated by great distances. Imagine creating two entangled photons whose polarizations are uncertain
You on a
until
roll,
measured.
little dude.
One might end up polarized vertically, the other horizontally. But they don't decide ahead of time who gets which. They stay in a shared quantum state, a superposition of all possibilities. Only when you measure one does the outcome become definite, and at that moment, the other state becomes definite too. Instantly, no signal, no delay, no chance to communicate. If you measure one photon in Paris, the other, let's say it's in Tokyo, responds at that very moment, as though the universe just updated both of them simultaneously. This is what Einstein famously called spooky action at a distance. Einstein wasn't fond of spooky things. He believed firmly in locality, the idea that physical processes at one location can't instantly affect things far away. It's a cornerstone of relativity. Nothing, not even information, travels faster than light. The idea that two particles could coordinate outcomes instantaneously without exchanging a signal made him deeply uncomfortable. In 1935, Einstein, along with Boris Podolsky and Nathan Rosen, published a paper challenging the completeness of quantum mechanics. They argued that if quantum mechanics allows for such instantaneous connections, it must be missing something, some hidden variables tucked behind the scenes, determining the outcomes all along. To Einstein, the universe should be predictable, orderly, and perhaps most importantly, local. But decades later, experiments began to confirm what quantum theory had predicted all along. Entanglement is real, and those hidden variables, they never showed up. In the 1960s, physicist John Bell devised a testable mathematical inequality, now known as Bell's theorem, that could distinguish between quantum predictions and hidden variable theories. And when physicists performed these experiments again and again, quantum mechanics won. Entangled particles do behave in ways that can't be explained by local hidden variables. The results are random, yet perfectly correlated. It's as if the particles share a private script, one that remains unwritten until the curtain rises, and they improvise together with eerie perfect timing. Still, this doesn't mean you can use entanglement to send messages faster than light. That would break causality, and thankfully, nature prevents it. While entangled particles react instantly to each other's measurements, the outcomes are fundamentally random. You can't control what result you get when you measure your particle, which means you can't encode information in it. The instant connection is real, but it can't be used for communication. It's like two people flipping coins on opposite sides of the galaxy. Each result is random, but somehow, when one person flips heads, the other always flips tails, and neither of them knows which it will be until they flip. They aren't sending messages, they're just in sync in a way that defies space. What's truly strange is that this connection doesn't weaken with distance. You could separate two entangled particles by the width of a room, a continent or a light year, and the entanglement would remain. There's no known limit. In fact, physicists have entangled particles over distances of hundreds of kilometers using satellites, and the results continue to uphold quantum theory. But what exactly is entanglement? Is it a kind of invisible tether? A shared identity across space? A subtle form of information smeared between particles? The truth is, no one's completely sure. Different interpretations of quantum mechanics offer different perspectives. Some see entanglement as a reflection of information, what we know about the system, not the system itself. Others see it as evidence of a deep, non-local fabric to reality. There's even a school of thought that entanglement isn't just a quirky quantum trick, but a fundamental feature of space and time themselves. Some researchers have proposed that space-time, the very geometry of the universe, might emerge from networks of entanglement between tiny quantum bits. If that's true, entanglement isn't something that happens in space. It's what holds space together. That's a bold idea, and one still under investigation. But it hints at just how central entanglement may be, not just to particles, but to the nature of reality. And like many quantum now a cornerstone of cutting-edge technology. Einstein may have disliked it, but even he couldn't deny its mathematical consistency. And while relativity and quantum mechanics still haven't been fully unified, both remain astonishingly successful in their respective realms. Entanglement reminds us that the universe is not simply a collection of independent objects bouncing around. It is a deeply interconnected web, where even distant elements can be parts of a shared whole, where separateness is, at times, an illusion. It's not something we see in daily life. You don't wake up entangled with your neighbour or find your coffee reflecting the state of someone else's spoon. But at the tiniest levels, this silent partnership between particles is quietly humming away everywhere, all the time. And maybe that's the strangest part of all, that even in a universe of stars and silence, of vast distance and emptiness, there are still echoes of togetherness, instant, invisible, and unshakably real. There are few animals in science more famous than Schrödinger's cat. This curious feline has become the unofficial mascot of quantum physics, a creature trapped in a thought experiment so peculiar that it's often mistaken for satire. And in a way it is. It was never meant to be taken literally, but like all good metaphors, it touches on something deeper, a quiet discomfort at the heart of quantum mechanics. The story begins in the 1930s when physicists were grappling with what quantum theory actually meant. The math worked, the predictions were accurate, but what was it saying about the world? Was the wave function a real thing? Did particles really exist in multiple states until they were measured? Or was this just a tool for calculating outcomes? Erwin Schrödinger, already famous for his elegant quantum equation, was deeply skeptical of how far some physicists were willing to push the idea of superposition, especially when it came to measurement. In his view, there was something fishy about applying the same rules that governed electrons to everyday objects, like, say, a cat. So he posed a question, a dark, playful question. What happens if you take the weirdness of quantum mechanics and scale it up to something you can hold in your arms? Imagine a sealed box. Inside the box is a cat. Alongside the cat is a tiny radioactive atom, a Geiger counter, a vial of poison, and a trigger mechanism. If the atom decays, something quantum mechanics tells us happens at random, the Geiger counter detects it. The trigger breaks the vial and the poison is released. The cat tragically dies. But here's the twist. Quantum theory tells us that until we observe the atom, it exists in a superposition of both decayed and not decayed states, which means the entire system, the detector, the poison, and yes, cat, should also be in a superposition. The cat is both alive and dead. Not metaphorically, literally, at least according to some interpretations. Of course, no one has actually put a cat in a quantum box. Schrödinger wasn't proposing an experiment, he was making a point. He found it absurd to think that a cat, an animal with whiskers, warmth, and a clear preference for naps, could exist in such a blurry, undefined state. It wasn't just strange, it was nonsense. And yet the idea stuck, partly because it captured the essence of quantum indeterminacy in a single, unforgettable image. A cat that is both dead and alive until the box is opened. That's a powerful way to express what it means for a system to remain unmeasured. It's not about indecision, it's about possibility. Until observation collapses the wave function, the system contains every outcome, all futures, all states, simultaneously. Schrödinger's cat isn't really about cats. It's about what we're allowed to say about the world before we've looked. In quantum mechanics, observation plays a central role. Before you measure a system, it exists in a cloud of probabilities, each possible state encoded in the wave function. But the moment you interact with it in a way that extracts information, that cloud collapses, the system picks a state. One possibility becomes real, all others vanish. But here's the tricky part. What exactly counts as a measurement? Is it the presence of a conscious observer, a mechanical detector, an interaction with the environment? Different interpretations give different answers, and that ambiguity is part of why the cat still gets so much attention. It forces us to confront the fact that quantum theory, while breathtaking, and measurement simply reveals what's already latent in the system. Others prefer probabilities as we go, or are we simply riding the wave, surfing on probabilities, never quite sure where the next collapse will take us? In the end, Schrödinger's cat isn't just about life and death, it's about knowledge and the strange dance between reality and observation. It's about what it means to say something is, when the very act of saying so might change. And yet still show up on the other side. No smashing, no breaking, no squeezing through cracks. It simply appears as if it decided the obstacle wasn't quite as solid as it looked. This phenomenon is called quantum tunneling, and it's one of those effects that makes you blink, rub your eyes, and wonder if the laws of physics are having a laugh. The tunneling is very real, it's measurable, predictable, and fundamental to how the universe works. And surprisingly, it all comes down to probability. To understand tunneling, we need to revisit the concept of wave functions. In quantum mechanics, particles like electrons aren't just little dots zooming around. They're described by wave functions that represent a spread of possible positions. These waves can extend across space, fading gradually instead of stopping abruptly. This means that even if there's a region the particle technically shouldn't be able to reach, the wave function might still stretch into that forbidden zone, albeit faintly. Now, imagine a particle approaching a barrier, a region with more energy than the particle itself has. In classical physics, this would be a hard stop, game over. But the quantum wave function doesn't vanish at the barrier. It tapers off, like a whisper fading through a wall. And if the wall isn't too wide or too tall, that whisper can make it to the other side. The particle might not have enough energy to climb over the barrier, but its wave function can tunnel through, and if part of the wave function makes it to the other side, there's a small but non-zero probability that the particle itself will show up there too. It's not magic, it's math. This idea sounds abstract, but it has very concrete consequences, especially when you shrink your thinking down to the atomic scale. Take radioactive decay, for example. Some atomic nuclei are unstable, and one of the ways they become stable is by ejecting particles, like alpha particles made of 2 protons and 2 neutrons. These particles are trapped inside the nucleus by a powerful nuclear barrier. According to classical physics, they don't have enough energy to escape, but they do escape, constantly. And quantum tunneling is the reason why. Inside the nucleus, the alpha particle's wave function stretches toward the edge of the nuclear potential barrier. Even though it's unlikely, there's always a chance the particle will tunnel through. Over time, that small probability adds up, and eventually the particle pops out. That's radioactive decay in action. Without tunneling, many elements would never decay, and nuclear physics as we know it would grind to a halt. Tunneling is also critical for the most important energy source in the universe, nuclear fusion. In the cores of stars, hydrogen nuclei are crushed together under immense pressure and heat. But even with those extreme conditions, they don't really have enough energy to overcome the electrostatic repulsion between their positively charged protons. According to classical calculations, fusion shouldn't happen nearly as often as it does. Yet stars shine, and tunneling explains why. At those high temperatures, hydrogen nuclei get close enough for their wave functions to overlap. There's a tiny chance that one will tunnel through the repulsive barrier and fuse with another. Multiply that tiny chance by the unthinkable number of particles in a star, and you get a brilliant sustained fusion process. The furnace that powers everything from sunshine to supernovas. And it's not just distant stars that benefit from tunneling. We use it right here on Earth, in labs, in factories, even in experimental computers. One elegant example is the Scanning Tunneling Microscope, or STM. This device allows scientists to visualize surfaces at the level of individual atoms. It works by bringing an ultra-sharp tip extremely close to the surface of a material, just a few nanometers away. At that distance, electrons can tunnel between the tip and the surface. By measuring this tunneling current, the microscope builds up an incredibly detailed map of the atomic landscape. What's remarkable is that the STM doesn't touch the atoms it's imaging. It's relying entirely on tunneling, on the ability of electrons to slip quietly through empty space, across a gap, and into a detector. This non-contact technique gives scientists a way to peer into the quantum terrain with stunning precision. Tunneling is also at the heart of certain types of electronic components, like tunnel diodes and quantum dots, and it's a looming factor in the future of computing. As we shrink transistors to ever smaller sizes, we're running into quantum limits. At nanometer scales, electrons can tunnel through barriers that were once considered solid. It's as if the walls in our circuitry are starting to let particles sneak through when they're not supposed to. This presents both challenges and opportunities. On one hand, it creates noise and unpredictability in traditional electronics. On the other hand, it opens the door to quantum technologies that use tunneling rather than fight against it. At its core, tunneling teaches us something profound about the nature of reality. We often think of the world as made of hard boundaries. A particle can go here but not there. A wall is a wall. But the quantum world is more nuanced. Barriers are not impenetrable. They are probabilistic. They are suggestions, not absolutes. And while we might find that unsettling, it's also strangely elegant. Because of tunneling, particles are not confined to the straight paths we imagine. They can cheat, slip, blur through the cracks of logic. They remind us that the universe is not a machine made of perfect gears, but a shimmering tapestry of likelihoods and possibilities. The tennis ball still bounces off the wall, but the electron, the alpha particle, the photon, they might just glance at that same wall and say, "I think I'll take the shortcut. And somehow nature lets them. In everyday life, we think of nothing as, well, nothing. The absence of stuff. An empty room, a blank sheet of paper, the space under your bed where socks mysteriously disappear. And when we extend that idea to physics, we often picture the vacuum of space as a perfect void. A cold, silent expanse with absolutely nothing in it.